I would like to use a brute force technique to generate a power series representation for f, set about x equals 1. In other words, I would like to re-express the output as this sum. Now, of course, the key here is I need to find those coefficients. But recall how we just proved that C sub n can be expressed as such. So let's find those numerators. Now, I've differentiated a few times with my function f. And so I suppose that implies the following. Of course, with the next derivative, I'm going to introduce a coefficient of 7 in this numerator and an extra factor of 2 downstairs. Kind of suggestion to me that there's a pattern to this nth order derivative evaluated at x equals 1. Would that be something's negative, whose numerator is 1 times 3 times, okay, you know what, this isn't going to work. I just don't have the board space. Let me try that one more time. This is suggesting that the nth order derivative, evaluated at x equals 1, is negative, fraction, has a numerator with factors 1 times 3 times 5 times all the way down to the last factor. But if you look at those factors upstairs, the understood 1, 3, 5, and the next will be 7. There's a linear progression by 2. So last factor is going to be certainly 2n plus something. To figure out what the something is, notice with the fourth derivative, that last factor upstairs is 5. But when I plug 4 and 4 in right here, I get an 8. So to force inside the parentheses to be an 8, question mark must be minus 3. All over a denominator that has as many factors of 2 as I have order of derivative. So that's what f sub n is. And C sub n is certainly going to be that. All over n factorial. Meaning, of course, my power series representation is going to be the sum as n range from 0 on up. I'll pull out the negative coefficient. Here's my C sub n, just copying what I have. Times my x minus 1 to the nth power. But sometimes the pattern to generate the C sub n doesn't quite come into effect with a few of the first finite number of terms. So let's just double check this. Because technically speaking, the very first term should be just this. And when I plug 0 in for n, I'm getting 1 downstairs, getting 1 upstairs, but I'm getting the lowest value of 1 times a higher value that's negative, which is not bigger than it. So certainly this pattern is not working when n is equal to 1. So I'm going to shave off the first term. And with this expansion, that first item, the first term really should be this, times x to 0 power if you like, or x minus 1 to the 0 power. Now let's see if that's going to work for n equals 1. When n is equal to 1, I really should have a negative 1/2 coefficient out in front of the x minus 1 parentheses. Let's see if I get it. When n is 1, here's a 2, here's a 1. The numerator goes from 1 to, well, when I plug 1 in for n, it's still negative. And so technically speaking, oh, you know what? I might get saved because of the negative sign out front, but I don't. So here too, everybody, I'm getting really nervous. Technically speaking, when n is equal to 1, the smallest value appears 1. The larger one is going to be negative. It's not fitting the pattern. I'm stuck. And so let me go ahead and shave off the second term as well. Now the second term should be this. F prime 1 over 1 factorial times x minus 1 to the first power. Since I already found that to be f prime divided 1, then I guess my next term, or grouping I should say, should be minus 1/2 times x minus 1 to the first power. Now I do think the next term should be f double prime of 1 all over 2 factorial times x minus 1 squared. Or shall we say, is that going to give us a negative 1/4? No, it's going to give us negative 1/8. X minus 1 squared. Let's just double check that I generate that when I add n at 2. So let's see, I shaved the first term, I shaved the second term. Now let's see what happens when n is equal to 2. So plugging 2 in front downstairs. 2 squared times 2 factorial is my 8. Got a negative sign up front, so that's there. My numerator starts at 1, but ends all the way down to when I plug 2 in front here, which is also 1. I start at 1, I end at 1. So the numerator is just going to be 1 itself, which is exactly what I need. And likewise, if n is equal to 2, I have indeed the correct exponent. So I do think then from n equals 2 on out, that really fits the pattern of what this coefficient should look like. Now, maybe I should provide an example where it's not necessarily the case that I generate what the power series looks like in terms of an infinite collection of terms, because I admit I'm very contrived with this example. It was really easy, even though I erased it, to differentiate repeatedly. Sometimes the differentiation process a bit of more of a work, and so sometimes I only want to grab the first few terms of this Taylor series. Anyway, that's my first example of creating a power series, or if you want a Taylor series, using my brute force technique.